Okay, so lab issues. Having any?
I'm still trying to figure out the counting, the visible stuff. I don't know.
I can only give guidelines on that. I can't tell you exactly what you're supposed to do.
Like the totals number for the count that I got was small number, not what you had in the example. So I don't know if I'm right or wrong.
So what are you putting into the tool to get that?
I put the BTBM something, and then I put the points. Is it point lines? Point line.
Points, yeah.
Points.
Yeah.
Yeah.
Yeah, point source.
Yeah, that's what I put. And then I put one for the Z text.
Yeah, it sounds like you're running your viewshed analysis on the points and not the line.
Yeah.
Yeah, you should run it. You should be running it on the line.
Oh, okay.
So the value you're going to get is going to be very different because you're asking the viewshed tool, hey, what places can I see from these n points, right?
Yeah.
Instead of what parts of the landscape can I see along this road.
Oh, okay.
Yeah. So, because the idea is, you go to that particular location for leaf peeping, right? Or to see this beautiful environment, whatever it might be. And if you were to go look at that landscape from those points, you'd be standing next to like sewage outfalls, or because that's what those points are. So you probably wouldn't want to go there and see the beautiful mountains, right? Any other issues? So probably you'll get the right.
So I have to pick a highway.
Yeah,
okay.
Yeah, and it'll take 50 minutes or so to run. 50.
Yeah, for points, it took me like 15 minutes or 20 minutes.
Yeah, it'll be easily double that for the line.
Oh, okay.
So, don't run it 10 minutes before class starts.
Yeah, I know. I will finish this weekend.
Cool. Things going well for folks otherwise? Any other questions about the lab?
Threshold
So you've got two data layers. This is a good question. You got two data layers, right? You've got the output, that flow accumulation layer, and then you have streams. Right? That's one of the layers in there, rivers, whatever. I don't know the name of it off the top of my head. And if you bring them up, that flow accumulation layer might not look like much. You could invert the color scheme, like go from, instead of low values being black and light areas being white, you could flip it around, you might see a little more. But what do you notice about that flow accumulation layer? Notice anything when you look at it? What does it look like? If you like zoom in on the side of a mountain. I wish I had it up. I don't think I have it on this computer. Well, it kind of looks like a stream network, and that's what you're trying to recover from it. And you also have a stream network that was actually collected by people going out in the field and mapping those streams. So, but to create the stream network from the flow accumulation map, you have to come up with a threshold value and put it into that tool con, right? I think that's what I have you doing. And so that accumulation, what's the number in there? In each one of those cells, what's the number? Each cell has a value, right? So let's say that the river is flowing this way. Which one of these cells is, well, first, what are the values in these cells? Nobody's written up their lab report yet? You don't write your lab report as you go? Nobody's looked up the flow accumulation tool? So, I'll be sure to read those sections of the lab reports very carefully. Basically, flow accumulation puts the number of pixels that flow into that pixel as the value. So let's say that this is the highest point in the landscape, right here, right? How many pixels flow into that cell? That pixel? No pixels. This is the highest point in the landscape, right? Then this one pixel flows into it. This pixel does, right? This one, 2 pixels flow into it. 2. This one, 3, and 4. So eventually, on a big landscape, you can get down to a pixel that has the value of 1,897,247, right? All of the pixels in the landscape flow into it. We call that a pour point. But anyway, what you're doing there when you pull a threshold up, you're saying, well, as long as 4,000 pixels flow into this one cell, 4,000 or more pixels flow into it, then that's a stream, right? That's what you're doing when you threshold that, when you come up with a threshold. And how would we come up with that threshold? There are a lot of different ways, but one of the most straightforward would be to check out the landscape and see where it looks like streams might actually exist, right? And then pick a number somewhere around that in your flow accumulation map. So if you bring up your streams layer, you can actually see where streams exist, and you might be able to come up with a flow accumulation value that generally corresponds with the ending point of those streams, right? So that's what I would do if I were in your situation. Open up the streams layer, put it on top of the flow accumulation layer, right? And then use the identify tool, that circle, blue circle with an I in it on the toolbar. Click on the end point of the stream, and then check out what the pixel value is in that flow accumulation map, and use that as your threshold value. That would be my tip. You could do it other ways too, though. You could say, well, I think that given that the pixels are this size, I think if you you were to pour a gallon of water on 500 pixels, right? That would be 500 gallons of water. That would create a stream. So I'm going to put my value of 500. But whatever you decide, make sure to make a note of it in your lab report.
So are we trying to figure out at what variable we eliminate the little branches off the main?
Basically, when you pick a threshold value, you're saying all the other drainage that happens, that's just surface runoff, right? So if you pick a value of 800, say, and I'm just pulling these values out of where. I don't remember. Actually, I do remember now that I think about it what a reasonable value would be, but I'm not going to tell you for this particular landscape. You're basically saying, like, I could pick a value that's so low that the entire landscape is a stream, but that's not very useful, right? So, you're picking a point where you're saying, anything where fewer than this many cells drain into it, that's just water running over the surface of the earth, just kind of runoff that happens. And you need to have so much runoff before it becomes a water feature. Right. Any other questions about that? I'm still writing your exam, so I don't have that set up yet. When you do take it, you'll just log into Blackboard as normal. It'll be right in the course content area, pop thing. You'll have a little blurb about what it is, how many questions are on it, how long you have to complete it. Remember, you got to do it in one setting. It'll be open at 7 a.m. on Friday, close at 6 p.m. There'll be one essay question, one kind of open answer question, and everything else will be true, false, or multiple choice. Okay. A couple words about how I write questions. I will sometimes have multiple choice true, false questions. So what's that? That'll be, what's a good example? All geographic data should have a projection and coordinate system. And then true, because otherwise you don't know where those data are. True, because projections are necessary for blah, blah, blah. False, because some data are not projected, they're merely geographic coordinates. False, who the heck cares about spatial data anyway, right? and then you'd have to pick the best answer from that. Now, there are actually two correct answers in there, but only one will actually get you points, right? True, because actually there's only one in that case that's correct. False, because some data don't have a projection, right? So remember, yeah, you have to have a coordinate system, but actually you don't need a projection. You can have geographic data that are technically unprojected, but they end up looking strange, like that Indiana, right? So you might run into a question or two like that, and sometimes that throws students for a loop. If I try not to write tricky questions. If there's a question where you're asked to provide the not, right, I'm going to try to make not pretty clear in the sentence. You know, like which one of these is not data measurement type, right? And you know that'll be capitalized not. I might bold it if I remember to, but it'll clearly jump out at you. It won't be one of these things where it'll like, well, there's that weasel word, and that's about it.
Don't have a class Friday, right?
No, you don't have a class in the classroom. You just take your exam at a time that's convenient for you during that day. Okay, let's talk about spatial pattern analysis. This kind of extends a little bit from what we were talking about on Monday. What do you see here? What are you looking at behind the title slide here? Yeah, the satellite image of forest. Probably no big surprise, it's the Amazon. But you know it's forest because it's a natural color composite, green's forest. And these white areas, what do you think these are? Some of them are clouds, that's what these white areas are. But these rectilinear white areas are deforested area. They're actually people's farms, small farms. They're growing corn or rice or beans, or they're ranching cattle. Okay, so this would be a family farm, probably about 50-acre farms, most of these. And I can talk about that because I've been near this place. I haven't actually been to this place. But we can actually look at the pattern and match it to known patterns and come up with a good guess as to what might be going on here. And so part of pattern analysis is actually what we call landscape analysis or even landscape ecology. But today we're going to talk about the concept of pattern analysis more generally rather than certain applications. Okay? Basically, pattern analysis, when you kind of boil it down to its essence, is really how do my observations compare with some theoretical ideal, okay, in terms of their spatial distribution. So remember we talked about spatial distribution earlier in the semester, and you can have data points which are clustered, right? That would be they're all kind of around an area. What would be a good example of a human phenomena that involves clustering? Cities, exactly. So, and Indiana is a great example of that. Like, maybe if you go to a place like, the East Coast, it kind of feels like there isn't any clustering. It's just one huge city. Or if you go to like the coastal California, it's like one huge city from like San Diego up to San Francisco. But come to Indiana, and yeah, it's clustering. You've got a town, and then a lot of farming and rural area, and then another town. Right, so we cluster around. So that would be one point pattern or one data pattern. There's also dispersed. And the perfect dispersed phenomena would be one where, it almost looks like a checkerboard, right? Where your immediate neighbor is never just like you. So, say if you were to go to a perfectly dispersed neighborhood and look at incomes, you'd have a rich person living next to somebody in abject poverty living next to somebody who's absolutely rich, right? Don't see that very often, especially not in this country. Can you think of any phenomena which are dispersed in nature? This one's tougher. I often to think in the wildlife realm. So you have like top-level predators. Could be a bald eagle. Could be a mountain lion. They don't really like to live next to others that are competing for the same resources. In fact, they have very big territories and they're very, very territorial. So that could be a good example, right? And then there are random patterns. Random patterns tend to be the result of natural phenomena, although you will find some human behaviors being somewhat random spatially. But in this case, you'd have pretty much no organization spatially of the phenomena you're looking at. And so in pattern analysis, we're talking about either how much does my pattern that I'm looking at right now differ from this ideal of clustered, dispersed, or random, right? And maybe are there areas which are very different from the expected pattern? So you either saying, I expect this phenomenon to be random, does it actually match random distribution, random spatial patterns? Or you could be saying, how much does my pattern actually differ from random? So you could say, I expect it to be clustering. Clustered, is it, right? Or you could say, assuming this is random, does it match random? Kind of you can approach it from two different directions. So clustering, like economic activity or towns. Dispersion, maybe top-level predators. Random distributions or spatial distributions tend to be the outcome of natural phenomena. Although, like I said, not always. Can you think of any random spatial distributions that human beings create? It's pretty hard. I have trouble with it. All right, one of the easy ways of doing this kind of analysis is called nearest neighbor analysis. And essentially, let's say that you have some distribution of data points, and instead of putting this into latitude and longitude coordinates, let's just go in an XY Cartesian coordinate system, right? So point A is at 1, 1 approximately, right? 1 unit in Y and 1 unit in X. Actually we have the table here, right? In X it's 1.3, in Y it's 0.9. See how that works? How my data distributed? Looks like something from a, nightmare calculus problem or something. And so we've got our data set, and we can also, using that data set, come up with the nearest neighbor that each point has, right? So what's the nearest neighbor of point E? D, right? You know that because it's in the table, but we can look at it here. Some of them might be a little harder, like the nearest neighbor of point A. According to the table, it's B, but looking at it, I'd almost call E, right? Guess not. Guess we all need new eyeglasses or something. But basically, you determine this nearest neighbor status intuitively, right, by Euclidean distance. You can calculate that pretty easily in a computer. And, we're doing that visually right now. When we say, oh, the nearest neighbor to D is E. Or the nearest neighbor to G is D, or I guess F. Right? And anyway, so then you can actually measure those distances and sum them up, and we can calculate average nearest neighbor distance. That's not too difficult. You sum up, how would we calculate that average? The equation's down here, but it makes it look way more complicated than it is. What's an average?
Sum of all the values and then divided by the number, one number.
Yeah, so how would we calculate nearest neighbor distance? Sum up our nearest neighbor distances and divide by the number of data points, right? And so we'd end up with our value, our nearest neighbor distance. What does this tell you, this value tell you? if all of your points were clustered right here, would your nearest neighbor distance be higher or lower? Your average nearest neighbor distance be higher or lower than it is for this distribution? It'd be much lower, right? Nearest neighbor distance might be like 0.2 or something like that. Whereas if you had all of your points like spread out evenly around the edge here, you know, it might be higher, right? Or you could get so that could give you some information about the average distance between points, essentially, in your data set, between locations, right? What would happen if you clustered them all, half of them here and half of them over here? Would nearest neighbor distance really tell you that much? No. It actually might end up with a value similar to the one that you get calculating it for this distribution. Essentially, you would be, because you've got them kind of dichotomously clustered, right? You're not getting at how clustered these things are, or if they're clustered. You're just kind of getting at the overall layout, how close a neighbor is. Yeah.
So what would the 19.2 like represent?
This value here?
Yeah.
That's the total neighbor distance. It's
So
just...
So you could use it like if you're doing a map, like different neighborhoods.
Yeah, really what you're interested in is the average for the average nearest neighbor distance. This is just a step along the way, summing that up. But you could use that sum, like let's say you're a farmer, right? You want to figure out, well, if I if I start my farm here, am I going to be able to get my beef cows to market, to the slaughterhouse, right? Is that going to be a problem? And you could start evaluating, say, county by county, the state of Kansas, right, or Colorado, wherever you're raising your beef. And you could put together for each county the locations of slaughterhouses and come up with this total neighbor distance, right? And obviously, you want that value to be smaller to get your cattle to the slaughterhouse, or whatever might be.
There is an outlier. Is it better to just eliminate it so we can get a more accurate numbers?
Like, let's say that you had a point hanging out like way up here.
Yeah, or something. Would it be better?
Well, it depends on what you're using this analysis for. If you're using it to get the overall distribution of points, like in this case, like if you're deciding, I want to cite something here, right? Or I'm trying to figure out how close it would be for me to get to something I need to get to. You probably wouldn't want to, because that outlier would be important. And it would bring your average nearest neighbor distance up, but that's okay because you're trying to say, hey, look, this isn't, the distribution here is more wide-ranging, it's wider than it would be if you removed it. If you're looking at just, like, let's say you're looking at here's Terre Haute, and you're trying to say, I don't know, gas stations, right? Probably if it was an outlier up here, it might actually bias your analysis, and you probably wouldn't want to include it in your data set. But you wouldn't make that decision after doing nearest neighbor. You'd look at the distribution probably and be like, that's an invalid observation. I can get rid of that. So you'd be doing that way back at the data cleaning stage. So yeah, it's a good overall picture, nearest neighbor distance, and it's easy to calculate. But honestly, it doesn't tell you all that much. It just tells you whether you're looking at a big distance between points or a small distance between points. We can actually, though, go beyond just looking at area, right, or the distance between neighboring points. So we actually assume if the pattern's random that we'll see something like this, that a random distribution, where did I put my thing? A random distribution would be expected to have some relationship like this. 1 over the density of points. So you take your whole area, right? How would we calculate density of points? It's actually up there. It would be the number of points, so n, over the total area. It just gives us our density of points. And so in the last example, we had 100 square units, right, because it was a 10 by 10 grid. And we had 7 points, so our point density is 0.07, right? Well, if we plug that into this equation, we end up with a value which we call little r, really. And that is the, basically the, let's see, what would I call this? It's the nearest neighbor index, but it's not the unstandardized version. That's what this first r is, the result of this equation, right? Why is it unstandardized? Well, it says here, right, the maximum value for a perfectly dispersed pattern of points is actually not constant. It's related to that density of points. So if you had a higher point density, you'd end up with a different R number. And so we actually have to standardize it using this equation here. Basically, you take the output of this and standardize it by the non-ratio, like a non-ratio number there. And you end up with an adjustment. But notice the adjustment's not huge in this case, 1.89 to 1.44. And essentially, using this nearest neighbor index value, we can actually start to get at whether our points are clustered or not. So if you have a value of 1, right, this is an index. So usually indices range, center around either 0 or 1 and range from 0 to whatever, or negative 1 to 1, right? That would be a 0-centered index. But in this case, that point distribution we looked at on the last slide, this one right here, right, has a standardized nearest neighbor index of 1.44, which is actually a more dispersed than random pattern, right? You could have perfectly dispersed would be like that rich person living next to a poor person living next to a rich person living next to a poor person example, right? That would have an R value that would be very high. Whereas a perfectly clustered, which would be all the points in your data set at the exact same point, the exact same location, that would have a value of 0, right? So we can actually begin to get at whether we have clustering going on, or whether our points are more dispersed, or whether they're completely random. And in this example, we're actually looking at a distribution of points here. It's not random. It's kind of more. There's actually not a random component to it. We're pretty sure it's just dispersed points across the landscape. Right? Random would be you could actually have clustering a little bit. So that's pretty useful, and just because you can start to characterize how your points relate to the ideal, right, of either clustered, dispersed, or random. Well, this is important because, remember, basically the discipline of geography and spatial analysis in general, no matter what your discipline is, relies on the idea of spatial autocorrelation. We've talked about this, right, a couple times now. Spatial autocorrelation is the idea that near things are more related than things that are far away. And I always give the temperature example, but it tends to hold true for lots of stuff, but not everything. Essentially, it would be neat if we could measure this, right? If we could measure it with some index where high values would that were clustered near other high values, so rich people living near rich people, right, would lead to a high, to some measure that would say, yeah, that's positive spatial autocorrelation. That's actually what we call it, positive. Not that necessarily is a good thing, right? You could have high levels of benzene in the groundwater right next to other high areas with high levels of benzene in the groundwater. That's not a positive thing, but it's positive spatial autocorrelation, okay? And then you might have also some indication of places where high values of something cluster next to low values of something. That would be the rich people living next to poor people living next to rich people case, right? And we call that negative spatial autocorrelation. Negative meaning that not necessarily that it's a bad thing, again, but that we're actually seeing the opposite of spatial clustering of similar values. Okay. And fortunately, for about 15 years now, we've been able to calculate two measures of this particular phenomena, spatial autocorrelation. One's Moran's I, and the other is Geary's C. Moran's I is a little bit more common, actually. And there are some good examples of how this works out. So in these 5 displays here, checkerboards we can call them, all right, think of these as maybe binary raster grids. What would binary mean? Made up of zeros and ones, with ones indicating the presence of something, rich people, right? Zeros indicating the absence of them, or whatever it might be. What do you think? Colts fans live next to Colts fans, typically, right? So that would be high positive spatial autocorrelation, right? You could have Colts fans living next to Colts fans. And you hit the boundary here, I don't know, near Cincinnati, and people like the Bengals or whatever it might be. So anyway, you have 32 cells. They're differentiated by color, right? And distribution differs. What are we looking at here? A. If you get to this side, your opponent has to king you. Right? This is your classic negative spatial autocorrelation. We have basically unlike things being found next to each other. And if we're measuring this by Moran's I, right? Moran's I is an index that ranges from, it's centered around 0, right? And you got -1 being extreme negative autocorrelation. What does autocorrelation mean?
Couldn't you just say the opposite, because they're still connecting colors? They're just going at the angles.
How so?
So maybe
They're
normal
going at a
distribution.
diagonal, black touching black.
Oh yeah, look at that, right? We've got some neighborage going on here.
Normal distribution, kind of.
So this would be where are you seeing a normal distribution? Okay.
White, black, white, black.
Yeah, so you kind of have your average is going to be the same in everyone. You're going to have the same, because this is binary data, right?
Yeah.
You're going to have a distribution that looks like basically half of your locations have zeros, half have ones. So your frequency, if you were to do a histogram, it would look like this. So here's number of times that value is found, and then your values. And it would look like this. "16 cells of 0, 16 cells of 1, right? But you're right, you would think definitely would have some extreme value, probably, right? But yeah, we'd actually call this what's the name for that in terms of distribution theory? It's not going to come to me. In terms of neighbor, though, right, you could make the argument that actually black cells are always found next to black cells and white cells are always found next to white cells in this distribution of points, right? And that's what Justin's getting at. And that's a great observation. What's the assumption here where I'm saying that there's no neighbors? Like that a black cell never neighbors another black cell? So looking at that, if you assume that cells connect only on the flat sides, right, and not on the corners, then there are no black cells neighboring black cells, right? So it's like this. If you take a 3x3 window, so I have to erase my purple drawing. Look at that. If you were to draw this out here on a 3x3 window, now I'll move myself in a second so you guys behind me can see. All right, here's your cell, and it's colored in, right? And here are the other colored in cells that are black cells, right? If you assume that neighbordom is only defined by the 4 cardinal directions, these flat edges, right? You only have 4 neighbors, and there's no black cells next to white cells. We would call that, I don't know if I'm talking about this in class. Rook's case contiguity. Why rook? Yeah, the chess position, the chess piece, the rook, right, can only move the castle, can only move in 2 directions, X or Y, across that chessboard. Contiguity just means neighbor, they're contiguous next to each other. However, we can also define contiguity as happening on these corners. And in that case, we also might call this 4 neighbor contiguity. So we could have 8 neighbors. What do you think you call that? Any guess? Well, but that'd be interesting. I actually don't know of any GIS software package that has bishop case contiguity, which would actually not be all 8. It would still be 4 neighbors, but would be only the corner itself, right? Because that's how a bishop moves, only on the diagonal. I've never seen that before.
Is it another chess reference?
Yes, it is another chess reference.
King's case?
Queen's case. I don't know why it isn't king's case, because it's not like you're moving as many cells as you want out on the diagonals. You're just moving 1. But yeah, it's queen's case. And then rook's case. So I think the reason why rook's case has never been implemented on a wide scale in the GIS is because, or bishop's case, because if the phenomena that you're trying to measure can accept neighbors being on the diagonal, there's probably no reason why you would then say, but not on the cardinal directions, up, down, left, and right, right? Like if you're saying it's acceptable that I would define my neighbors as being on the diagonal, right? There's probably no reason why you'd say it, but it's unacceptable on this slightly closer edge. But, so that's why you don't usually see bishop's case listed. But there's no reason why, if you come up with a reason why that should be measured, there's no reason why you shouldn't define contiguity that way. So, we're working with a 4 neighbor case definition of contiguity here. And part of that is because it makes the math easy. with 32 cells of two colors, right? We can divide up that 32 cell landscape so that 16 are black and 16 are white. Whereas you couldn't have that even number of each type in a landscape where you were using 8 neighbor, because these would have to be white cells. And then you'd have twice as many white cells as black cells to have the perfectly negative spatial autocorrelation. I'll say right now, having done some autocorrelation analyses in my day, that I have never come across anything that even approaches perfect negative spatial autocorrelation. I'm not saying that it's impossible or that such a thing doesn't exist out there. I'm just saying that it probably doesn't exist. Okay? So there's a difference between saying it doesn't and saying it probably doesn't. Yeah. I'm not going to say Bigfoot doesn't exist, but Bigfoot probably doesn't exist. So anyway, there's perfect negative spatial autocorrelation. And of course down here we have what we call perfect positive spatial autocorrelation, where all of our black cells are neighbors of each other, right? And all of our white cells are neighbors of each other. And so that would actually fall, it's not quite perfect because why? There's this row of black cells that has white cell neighbors. So you will, by definition, never measure perfect positive spatial autocorrelation, because some measurement has to have a neighbor that's not exactly like it. Okay, but you can come pretty darn close. Okay, and then we have kind of the middle measure, which would be neither positive nor negative spatial autocorrelation. And this sort of observation happens pretty frequently. So we do have a lot of black cells neighboring one another, but we have a lot of white cells neighboring one another. And you'll notice that that I value, that Moran's I value, is a 0. And that's basically saying, well, the clustering in one value offsets, that spatial clustering offsets the spatial clustering in the other value. And so you can't really say that most of your black values are clustered around each other, while the white values are not, right? You just kind of have a neutral, we call this neutral spatial autocorrelation. Basically, what that means is, if you were to think about it in terms of like walking across the landscape, that walking from one cell to another, you're just as likely to walk into a black cell in this case as you are to walk into a white cell. Just walking across space. They're not clustered next to each other. And you can have varying degrees of positive or negative spatial autocorrelation. Right? Excuse me. The Geary C measures the same phenomena of clustering, right? But there's a little bit of difference here. In cases where data are similar or regionalized, so like in this case, right, or in this case where their similar data are grouped together, Moran's I is going to have a value greater than 0, right? Whereas Geary C is going to be some value between 0 and 1. Now, what does that mean? Well, that means that Geary C actually fits on this scale, right? It actually fits on a different scale. 0 to 1 would be the scale. And that perfect positive spatial autocorrelation is going to have a value of 1, right? In the Moran's I context, you can actually calculate a spatial autocorrelation value of greater than 1. I've calculated them at 3 or more. And that just means that because you're looking at values here, right, and trying to correlate them in space, the math behind Moran's I just allows for the index value to go greater than 1, right? Whereas Geary C is constrained, basically. Uncorrelated, that would be neutral autocorrelation or a random distribution, right? In Geary C, it'll have a value of 1. In Moran's I, it'll have a value of 0. And then this negative spatial autocorrelation it'll have, in Geary C actually, it'll have a value greater than 1, I guess. I've never really used Geary C, so. It's not a very commonly used measure because Moran's I is seen as an improvement. And the reason for that is you can actually diagnose the statistical power of your Moran's I measurement, whereas Geary C, it's pretty hard to do that, given the math behind it. You don't have to know that for this class, but I want to give you the context for why you probably choose Moran's I, depending on what kind of analysis you're actually doing. Well, why would we care about these things? Let's put it into some concrete terms. Actually, this Moran's I statistic gets used a lot for trying to figure out what's going on in terms of things like healthcare, for instance. This is an example from Louisiana, and what we're looking at here are counties, essentially, right, that have either more claims to healthcare providers, or so that'd be above expected values, so more than average, or less than average claims, right? Really, it's not quite average; it would be expected. So, we know that people who live in certain counties or parishes of Louisiana are going to be more likely to need medical care than others, right? But we can look at places that get that have above expected medical service requests or claims and below expected. Notice above we've got a bunch of areas in northern Louisiana, and then below, and we're actually looking at this just based on the number of claims, right? And then notice how they cluster in space, right? So we end up with actually spatial clustering of above and below values. So in that case, parishes were divided into two groups because they don't talk about counties necessarily. Light green, so they'd be below the expected value of claims clustering. So what would that mean? One parish has high claims, whereas its neighbor has low claims. And then parishes above the expected value would be dark green. Basically, light green parishes have a dissimilar number of beneficiaries, so those receiving the benefits of a healthcare claim, than neighboring parishes, and then these dark green ones have a similar number, so they're like their neighbors. So let's go back to that. So these are places where there's a trend, right, spatially, and then these dark or lighter areas are those places where there's actually the opposite of a trend. It seems to be rather, actually the trend is there, but it's that one parish has high values and the other has low values. What might cause that in healthcare? So what do you think? Do we see more medical claims to insurance agencies here in Vigo County than they do in Clay County? Yeah, why? Couple reasons. Population. How many hospitals are there in Clay County? One. How many hospitals are there in Vigo County? Yeah, 2 or 3, right? How many doctor's offices are there in Clay County? N. How many doctor's offices are there in Vigo County? N times some number, right? We actually have way more doctor's offices of all kinds here in Vigo County. So you could look at these data and be like, well, there's a reason why one parish has high values of claims and others low values, because there's more medical services provided. Anyway, you can also start to look at clustering, and I know it's time to go, so I won't go too far, but you can see places where there's actually a significant clustering statistically of similar amounts of claims. Just to skip ahead, we can actually look at that in terms of crime here in Terre Haute. If you look at the Farrington's Grove neighborhood down south here, right? There were a bunch of vehicle thefts in 2008, right? But if you look at just the clustering of those vehicle thefts, there was a significant clustering down here south of Washington Street, right? We could look at just theft in general, and while there were thefts all over the neighborhood, which is kind of defined this way, there were highly significant clusters of theft in these locations, right? So a detective who might be looking at theft would be like, well, maybe I should go talk to some people around there, see what's going on. Maybe there's some unsavory tenants living in a house. Or you could cluster burglary. Notice we've got like 12 cases of burglary right here.
Where's that?
That's Center Street between Deming and Oak. And that's in 2008, obviously, so things have probably changed. But you can use these clustering and distribution pattern analysis techniques to really get at some pretty interesting things, like that can be used for real-world decisions. Anyway, it's past time, so feel free to go. I guess good luck on Friday, and email me as soon as you run into any problems if you do.
The questions are going to take from the notes in the book.
Yeah, you have class in the book. And there might be one or two that relate to lab, but it wouldn't be like, what were your results of lab 2? It'll be more like, in lab 2 you learned about this. How would you use it, or something like that.